different papers that are being given here at the meeting. The first one will be Understanding Local Luminous Infrared Galaxies in the Herschel Era from Jason Chu, who's at the University of Hawaii's Institute for Astronomy. He'll be followed by James Lowenthal from Smith College, who also happens to be one of our vice presidents. He'll talk on the brightest galaxies in the universe. Next up will be another one of our AAS vice presidents. It's just a coincidence. Jack Burns from the University of Colorado Boulder, who will be talking about banging galaxy clusters. And then, hey, no Snickers. And then we will have Benjamin Hoscheit from the University of Wisconsin-Madison, who will answer the question, do we live within a large local void? So with that, I will turn it over to Jason.
Okay, aloha everybody. Thank you for coming to my presentation today. So today I'll be talking about local luminous infrared galaxies in the Herschel era. So this is in conjunction with my advisor David Sanders, as well as collaborators at Caltech and IPAC. So why do we care about luminous infrared galaxies? Well, before the 1980s, we had no idea that this class of exotic objects even existed. So it wasn't until the Infrared Astronomical Satellite, or IRAS, in 1984 actually discovered a whole population of galaxies we actually had no idea existed. And so these are very, very bright objects, and these galaxies or galaxy systems can emit luminosities of up to trillions of the same output as our sun. So they're very, very bright. But the difference is they're emitting it in the infrared, and so we don't see them very obviously in the optical or in visible light. So many of these objects are found to be interacting or merging. And so this happens when the mutual gravity between two galaxies is strong enough that they come together and they collide, and they create this jumble of systems, or a cosmic train wreck, as sometimes we like to call it. So here's an example of kind of a time sequence of what a galaxy merger looks like, starting with stage A here. Oops, wrong way. You see two isolated galaxies, but then by stage B, they start to come together, and stage C, they start to coalesce into one galaxy, and finally in stage D, they are essentially one single object. And so these objects are also important because they're much more common in the early universe, simply because back then the universe was a little smaller, and so galaxies were more likely to run into each other. So our understanding of how they work in the local universe significantly affects our understanding of galaxy evolution in the distant universe, where the number of objects, the number of LIRGs, as we call them, are up to about 1,000 times more common. So for our project, we used the Great Observatory All-Sky LIRG Survey, where LIRG stands for Luminous Infrared Galaxies. And so these were selected from a sample, the same sample that IRAS detected in 1984. And so these are very nearby objects, so they're very easy to study, and we can study them across all different electromagnetic wavelengths, from everything from radio all the way up to optical, obviously infrared, UV, as well as X-ray. So we have data for most of these objects in a lot of different wavelengths. And so they represent galaxies going through all major interaction stages, as well as infrared luminosity evolution. So it's the evolution of the brightnesses of the galaxies. And so as galaxies merge, the process of merging can actually induce a huge amount of star formation very, very quickly, as well as the sun feeding of the supermassive black holes that reside in the centers of both galaxies. And so both of these effects can produce a huge amount of dust, and as well as dust heating. And so the dust gets very hot, and the dust needs to radiate that heat away, and so it radiates in the far infrared because its temperature is lower. And so this is what produces the intense infrared signature that we associate with LIRGs. So since the majority of the radiation is emitted in the far infrared, it is paramount that we directly measure their infrared brightnesses. So before Herschel, our ability to probe this far infrared brightness was very limited to either low resolution studies or high resolution but near infrared studies. And so both of these have certain problems with trying to predict the brightnesses at far infrared wavelengths with high resolution. So it's critical to study these galaxies in the far infrared with high resolution, because that's where they emit the most of their intrinsic luminosity. So To do this, we turned to Herschel, the Herschel Space Observatory, which was launched in 2009. And so the observations have to be made from space just because Earth's observation blocks all far infrared light. And so we have to go to space in order to do that. And so this spacecraft, the instruments on the spacecraft extends the wavelength coverage into the never-before-seen regime between far infrared radiation and sub-millimeter light. And so I'll get a little bit more into what wavelengths we're talking about in just a moment. So previously, the longest far infrared wavelength is about 160 microns, and the shortest sub-millimeter wavelength is about 450 microns. And so with Herschel, we can now see that interesting regime between 160 and 450 microns, and we can probe directly the processes that create the radiation at those wavelengths. And so it's important to note here that Herschel is the last in the long line of very famous infrared missions that has allowed us to better characterize the energy output of LIRGs in the far infrared, and that's because that's where they emit most of their, the bulk of their radiation. Okay, so let's talk about results. The published paper, we published an ATLAS paper full of images for the entire sample of galaxies within our sample. So it's about 200 objects. And so here we show an optical image from the Pan-STARRS telescope, also in Hawaii, on top of Haleakala in Maui. And this is a picture of a merging system in our sample called ARB84. And so you can see there's some obvious spiral structure in both galaxies, although the top left one is clearly disturbed and warped. And so that's because these two galaxies are beginning to merge together. And however, if we now turn and look at the Herschel image, you can see that it looks actually completely different. And so the dark dust lanes in the optical image that are very apparent now show up as a ring of a prominent ring of hot dust emission, and that's due to the hot star formation that's hidden from view in the optical, while the bright optical spiral features are largely invisible now. And so the nucleus of the smaller galaxy, which is on the lower right, also shines brightly, in fact even brighter than the larger galaxy to the top left. And it does so because it shines brightly because in the far infrared, the dust is heated by both the intense star formation as well as a growing supermassive black hole. So before before IRAS, we had no idea what some of these objects even existed. And so in order to kind of take a look at some general properties, we divide our sample into 6 different levels of infrared brightness, which I've shown here in 6 different graphs. So on the x-axis is the wavelength from 1 micron to about 1,000 microns on the right side. And so this is a very, very huge range in wavelength. So generally speaking, the near infrared is about 3 to 10 microns. The mid-infrared over here is about 10 to 40 microns. The far infrared is about 70 to 250 microns, and the sub-millimeter we consider to be about 250 to 850 microns. So just for a sense of scale, here is the location of, oops, sorry, I'm one ahead right there. So I've highlighted 100 microns because that's approximately the width of a human hair. And so we're talking about wavelengths that we can actually see with our own eyes. So when IRAS was launched, we then noticed that these objects existed. And so here we show that their brightness across the range that I have shown. And so the gray shading here represents just the width of the distribution of the objects. And so as we continue from 1984 into about late 2000, 2010, we've discovered more information in the mid-infrared as well as the near-infrared. And so you can see that the critical wavelength regime over here, beyond 100 microns, was never really probed very thoroughly. And so finally, with Herschel, we can actually probe that entire range. And you can see how it fills in. And so this now allows us to calculate many different physical properties, such as the mass of the dust emitting the far infrared light, the temperature of the dust, also star formation rates on scales smaller than the galaxies. So just as a summary, our Herschel observations we have a complete set of ATLAS images now available to the public. These are accessible, and you can visit our website below. And so we can now, using this data, accurately calculate many important far infrared galaxy properties that was previously impossible. And for those who like to use Twitter, this can be summarized in 140 characters as, we obtained the best far-infrared maps of local luminous infrared galaxies, allowing us to study galaxy properties previously impossible to do. Thank you.
Good afternoon. I'm James Lowenthal at Smith College in Western Massachusetts. Nice to see you all here today. I want to tell you about some exciting new results from Hubble Space Telescope, but it's actually a combination of many telescopes that contributed to this project. My collaborators are shown here at the University of Massachusetts, at our sister institution Inaue in Mexico, and at the University of Arizona. The title of my talk says it all. Hubble confirms that the brightest infrared galaxies are gravitationally lensed starbursts. This is a somewhat natural extension of the talk you just heard from Jason. We're talking about the same kinds of dusty starburst galaxies. They're just much further away. If I could just give you some quick takeaway points, and I'll summarize it at the end. We have identified the infrared brightest galaxies in the universe, scattered around the sky just the way the brightest stars in the sky are scattered around. What are the chances if you just pointed in a random direction, you would be pointing at one of the brightest stars? Not so great. You would have to look around to find them. We did that for the brightest galaxies, and it turns out, Hubble shows us, they are all gravitationally lensed, as we'll discuss in just a second. These images that I'm showing you, just a sample of 6 of them here, any astronomer looking at these would say, that's a lens, that's a lens, that's a lens. At least 8 of them show so-called Einstein rings. Those are the ring-like features you see here, and here, and here. Again, these have become common in Hubble telescope images now, and all astronomers would recognize, those are Einstein rings. So more in a second about what makes that happen. This is just to summarize really what Jason just said. In the nearby universe, if you take 2 galaxies like these, this might be, say, the Milky Way, and our sister galaxy, the Andromeda galaxy, and you crash them together, let them fall together by their own gravity, that collision will not only destroy the 2 spiral galaxies and produce a new galaxy that will be a totally different shape, but in the process, it will produce an enormous burst of star formation. Right now, the Milky Way is producing stars at a sort of quiet rate of 1 or 2 new stars per year. This collision that produces something like the galaxies we just heard about from Jason, so-called luminous infrared galaxies, that collision, the process might actually result in a starburst producing 1,000 solar masses, 1,000 new stars per year, or even more. Now, we see this in different stages locally. Again, this is sort of an early merger stage. This is a later merger stage, the famous Antennae galaxy, imaged here from the ground. The lower photograph showing these long so-called tidal tails. The upper right photograph showing a close-up with Hubble Space Telescope of the core of these merging galaxies. And you see not only the red light of hydrogen from star formation, but also that sort of brown fuzz everywhere. What's that? That is the smoky dust produced in the star formation process that is obscuring more star formation hidden inside this dusty cloud. It's like having a fire hidden by its own smoke. You might not be able to see the fire itself because of all the smoke. All right, so that's nearby. We have a pretty good handle on what makes so-called LIRGs and ULIRGs, ultra-luminous infrared galaxies, happen. Seems to be from crashing these dusty, gas-rich galaxies together. What about their more distant cousins? We have been successful at finding these super, super luminous starburst galaxies in the distant universe thanks to the help of the Planck satellite, which was launched largely to study the cosmic microwave background and did a spectacular job at that, but it also resulted in an all-sky survey in the far infrared and submillimeter wavelengths, which then let us go search the entire sky for the brightest far infrared sources. We cross-checked them carefully with Herschel satellite, the Very Large Array radio telescope in New Mexico, the WISE satellite, Sloan in the optical. Every wavelength we could that had deep images of that part of the sky, we cross-checked. We built up a catalog that produced images with objects we think were the right colors and brightnesses to satisfy being very, very luminous but distant galaxies. We then went to a telescope that UMass has built in Mexico with Inaue, The Large Millimeter Telescope, a soon-to-be completed 50 millimeter wave facility that let us measure the distances exactly to these galaxies. We were able to measure their redshifts, which tells us how fast they're receding, which tells us, because of the expansion of the universe, how far away they are, and therefore how far back in time we're looking. And this resulted in finally a target list of 31 of the very brightest infrared galaxies in the universe. And let me show you just one example. You see on the far left what it looks like in the Sloan Digital Sky Survey. Not very impressive, is it? Nothing there. In the optical, there is just nothing bright. But in the infrared, this is the spectrum here, similar to what Jason just showed you. It's a spectacular peak of emission, very strong emission here in the far infrared. That's how we found it. When we look with the Large Millimeter Telescope, our new 50-meter dish, soon-to-be 50-meter dish in Mexico, we get a strong detection every single time. Every one of our 31 galaxies came up with a very strong detection in the millimeter. That is the light from star formation reprocessed by dust. That's that smoky, dusty stuff hiding the star formation inside. And the numbers are very impressive. They turn out to be, as I said, they're not just LIRGs, they're 10 or 100 times brighter than the LIRG threshold. They really are the most luminous objects that we know of. And there is the redshift of this particular source, again, discovered, measured by the LMT, and that shows us the look-back time, 11 billion years back in time, compared to the age of the universe, 14 billion years. The problem is, we can't really tell from this image, the image in the lower right, what's going on. Is that a merger? Are there tidal tails? Are we crashing two galaxies together? Can't tell. It's just a fuzzy blob because in the millimeter and the far infrared, we don't have very sharp vision. To get a really clear picture, we need to turn to something like Hubble Space Telescope, which normally is not going to get a very good view of these objects because the optical is so faint. But in this case, we have really extreme cases, and there is enough light coming out in the optical to see them with Hubble. What do the images show? Well, they knocked our socks off. This is just a sample of the first 11. Our program, our cycle 24, which is the ongoing cycle of observations with Hubble, had 22 out of the 31 because some of them were being done by other groups. Our sample of 22 is still not done yet. This is just the first 11 to come from those 22, and one after another. Every couple of weeks I get a cool email that says, oh, you're about to get another image, and I just can't wait, and I download it as soon as I get it, and one after another has been a spectacular pleasure. This is a treasure box, a jewel box of cool new images. And again, one after another, you see Einstein ring, Einstein ring, Einstein ring, Einstein ring, gravitational lenses galore. This is a gravitational arc here. It's not a ring, but this is an image of our galaxy that has been stretched like spaghetti into this funny shape. That is not actually the true shape of the galaxy. These are all warped images of our distant galaxies. And we have added significantly then to the total list of known gravitational lenses without even trying. We did not set out to find gravitational lenses. We set out to study distant, dusty, starburst galaxies. But it turns out the brightest ones are all gravitationally lensed. Now, for perspective, this was the previous largest sample, still is the largest sample of known gravitational lenses, the so-called SLAC survey. They set out to find gravitational lenses, and they did a great job at it. And here, just by targeting the very brightest, most luminous infrared galaxies, we find more and more gravitational lenses, adding significantly to the tally. All right, gravitational lensing. How does that work? What's happening here? This is a cartoon artist's rendition showing Earth in the lower right, looking at a distant galaxy in the upper left. And the distant galaxy is sending out light in all directions, including those white light rays and the pink light rays. But notice there's something in between us and them. That something, in this case, is a massive cluster of galaxies weighing maybe 100 trillion times as much as the mass of our sun. Many thousands of Milky Ways worth of mass in that one galaxy cluster. And as Einstein showed, mass bends space-time. Mass tells light how to move. Light follows the warped, curved contours of space-time, curved by that massive presence in between, which means light rays from the galaxy that start off going in one direction will curve around and come in a different direction. That means that we at the Earth actually see light rays coming to us from the same galaxy from different directions. That means we see multiple images of the same galaxy spread across the sky, or maybe a single image smeared around in funny ways. Now, you've probably seen this before. You can see it in this image of one of the Hubble frontier fields, the galaxy cluster Abell 370. All the yellowish objects in this picture are member galaxies of the intervening nearby foreground galaxy cluster. All the bluish, long, skinny, linear features are distant galaxies whose images have been bent and curved and warped, like the view of yourself in a funhouse mirror, or the view of something on the bottom of a swimming pool that you see through the wiggly surface of the pool. You get this warped view, and that's what all the funny warped images are in that picture. Now, you might have enjoyed dinner last night at one of the many lovely restaurants in Austin, and after you finished draining a glass of wine, you took a look at the candle on your table through the wine glass. And you might have noticed that as you tilt the wine glass in different directions and look through the bottom of the wine glass, you get warped images of the candle. It's the same candle, it's just different images of the candle. And if you hold the glass just right, you might even line it up in such a way that you get a perfect ring of candle light. So you can see it depends critically on both the nature of the lens and how you hold the lens. This is exactly analogous to what's happening in space. Here is an example of one of our objects. We knew already that this one was a gravitational lens. It's called 9IO9, and the upper left photograph is an image made with the ground-based Canada-France-Hawaii telescope on Mauna Kea. And you can see it's got a red ring around a yellowish pair of objects. It turns out the yellowish pair are nearby galaxies. The red ring is the distant galaxy whose image has been warped into a ring. And we're able to build a mathematical model, a computer model. Here are two examples, Model 1 by another team, Model 2 by us, that pretty much agrees, that can explain this warping of space-time. But it's kind of a crude model because the data are so fuzzy and low resolution. Wouldn't it be great if we had a really sharp picture? Well, we do. Here's the new Hubble Space Telescope image from our program showing dramatically more detail. And one after another of our images comes up like this. This now allows us to make dramatic steps forward, which we're only beginning to do. As I said, we're only halfway through even collecting the data, but we felt we just wanted to share these spectacular new photographs that are exciting us so much. What can we do with them? We can use the images to unscramble the true shape and nature of the background galaxies, and we can do it with better precision than we could before. The beauty of gravitational lensing, even though it makes the images complicated because of the warping, it also makes the images brighter, and it makes them bigger. That means we can see small, faint details that we never could have seen before. Where before maybe we were going to see details only on the scale of a few thousand light years across, now we hope to see details in our galaxies on the scale of a few tens or at most 100 light years across. That should let us really get to the core of the matter. What makes these ultraluminous infrared galaxies work? Is it true that they are galaxies crashing together or not? Is it instead that there is gas flowing in smoothly? Are there channels of gas coming in while there are other channels of gas coming out? All of these are models that are proposed by theorists that we have not yet been able to test. We hope to be able to test those with our new data. To do that, we really need some color information. Color information will help us, that is to say, we have black and white pictures from Hubble, taken with only one band. We've applied for more time with different colors from ground-based and Hubble Space Telescope. That will really help us tell what's a foreground, what's a background galaxy. That will help us build the proper computer models to do this untangling. Now, I told you I keep getting little presents in my email. I got one while I was at this meeting. So nobody else has seen this yet. I haven't even shared this with my collaborators. I've seen it, but are you ready? Here we go. Okay, it's another one. It's another spectacular gravitational lens. My quick and dirty analysis is that the galaxy right in the middle is a massive lensing galaxy. That's the foreground galaxy. And the long curving smile on the right there is our submillimeter galaxy, warped into a long, thin, skinny spaghetti image by the mass of the foreground lensing cluster. It's the galaxy right in the middle is the wine glass, and the curve in the back is the candle. So now we have a new opportunity to study in great detail the candle in the background. So just to wrap up, here again, a sample of just 6 of the eventual 21 targets. We've identified the brightest galaxies in the sky. We've confirmed their distances. We've confirmed that they're massive starbursts. We've confirmed with Hubble that they are all gravitational lenses, with at least 8 new Einstein rings, probably 10 or 12 by the time we're done. And we are confident that this gravitational lensing will let us probe faint, small details that will let us address in a new and sensitive way what actually fuels these monster galaxies. And I just want to leave you with one final thought. I have, because of this project, a new perspective on the distant galaxies that I've been studying for my whole career. While we're studying only the tip of the iceberg here, only the very brightest galaxies, the fact that every single one of them is gravitationally lensed really makes me think again about all those deep fields that we see, those images of more or less blank parts of the sky that turn out to be not blank at all. When we study them deeply with Hubble Space Telescope, we find they're just galaxies layered and layered and layered back in space and time. We've known about that for 20 years. But of course what that means is there's always something in front of the galaxy, the distant galaxy you're studying. And that means all, or certainly most, maybe all galaxies are gravitationally lensed to some degree. Now, this is not really news, it's just news to me. Maybe you already knew this, but it just makes me think about it in a different way. Typically, we've tended to ignore that, except in cases like these, where it's just staring you in the face. It's so obvious. But I really think this is going to change my perspective when I go out and measure the shapes or sizes or brightnesses of galaxies that are not obviously lensed. We really have to think in new, subtle or more nuanced statistical ways about the degree to which gravitational lensing is affecting our view of the distant universe. It's basically that we're looking at the whole universe of galaxies through sheets of wiggly glass, whether we knew it or not. Thank you very much.
Well, James, you're a tough act to follow. Gravitational lenses, Einstein rings, lots of good things. But James mentioned, as part of his talk, clusters of galaxies. And that's what I'm going to speak with you about today. That's the formation and evolution of clusters of galaxies. They are the largest gravitationally bound systems in the universe. And they form via mergers between groups of galaxies and gas, very hot gas that emits X-rays inside these deep gravitational wells. And as you see in this numerical simulation, which is up this video of a numerical simulation that we've produced, is that these clusters form right here at the apexes, the intersection of these filaments that produce the cosmic web. And if this is running again, and if we look closely, for example, and here you see 2 clusters or 3 subclusters coming together, banging together, thus the name of the title of my paper, and coalescing. Energetically speaking, the kinetic energy associated with the accretion of these clusters is the most energetic event in the universe since the Big Bang itself. So these are very impressive. These are very massive objects. And the process of merging leaves some interesting observational signatures that we can study in the X-ray, the radio, and the optical part of the spectrum. So what I want to do today is talk to you about one such cluster that we have been studying recently as part of our larger sample of roughly 50 galaxy clusters. This is Abell 115. It's a pretty massive cluster. You see the characteristics up over here with the details. It has a mass that is in excess of 10 to the 15 times the mass of the sun. The X-ray emission, as I mentioned before, comes from very hot gas. In fact, in the color image that you see up here, the false color image, this is an X-ray surface brightness map made from 5 pointings with the Chandra X-ray Observatory. Overlaid onto that, the white contours is radio emission from the Very Large Array radio telescope, and this is data which has just been published recently by Bodian et al. in some of these VLA observations. The radio emission, as I'll talk a little bit more about, this has generally been referred to as a radio relic. And the thinking is that this is the residue of the merging process in which a strong shock, kind of like a bow shock that you have in front of a supersonic airplane, that accelerates electrons to very high energies near the speed of light, amplifies magnetic field, and produces this extended radio emission. So that's the general thinking, that these relics correlate with these merging clusters. In the X-ray, you can see these two clumps here. This looks like the components of two clusters that are in the process of merging, and I'll show you some further numerical simulations a little bit. It looks like the process goes something like so. They spiral together and eventually merge. So we're catching this cluster in a relatively early stage of merger. Okay, so that was what was known. Some of the new work that we've been doing is, in addition to creating this newly reprocessed X-ray surface brightness map, here's a version of that map now in which we smoothed it further so we can see some of the more extended structure. And you can see the hot X-ray gas emission literally fills the entire field. In addition, we've gone in and utilized some existing VLA data and reprocessed that with higher resolution, so that the cyan-colored contours that you see within the white contours here show us that there are individual radio galaxies within this broader relic of radio emission. There's one here where the arrow is pointing right now. This is 3C28. This is a strong radio source associated with the giant elliptical that coincides with this X-ray hot gas region here to the north. And then this head-tail radio source. And right at the top here where the arrow is pointing is a galaxy at the same distance as 3C28. And very faintly is some enhanced X-ray emission right at the leading edge here as well. So we've begun looking at some of those details of some of the individual radio emission within the arc that we see here. Now here's our new temperature map. So what my students and I have been working on, and my collaborators, is a new pipeline to construct high fidelity X-ray maps, X-ray temperature maps, by utilizing a gridding process and a supercomputer to calculate literally tens of thousands of spectra that are necessary in order to produce a temperature map like what you see here. So what we do is we fit the spectra. The emission is hot thermal emission. That fitting allows us to calculate a temperature, and from that we can reconstruct then the temperature distribution, which is what you're seeing out over here. Whereas the white is the hottest gas, and the black in here is the cooler gas. And
Sorry to interrupt. We're not seeing your arrow.
oh, really?
Yeah.
So that's not popping up. So let me try what James suggested here. So is that appearing now? Okay. I thought that it was. My apologies. So the hot emission is right in the very center here, and then the black is this cooler gas that we see up over here. So we were surprised by this X-ray emission. This is very hot gas lying within the center region between these two subclusters, which are in the process of merging. Very hot, about 170 million degrees Kelvin. In comparison to the cooler gas, which is about 50 million degrees. If you want to call cooler 50 million degrees, that's still pretty hot. But what is interesting is what is the origin of this very hot gas that we see in and over here. And then in addition, what's interesting is you can see some of the effects of the merging. That is, the cool gas in the center of this cluster, some of that has been stripped out, and you can see that you can follow this along a wake behind this cluster and this subcluster, and similarly behind over here. So one of the curious things is what is producing all of this complex temperature structure that we're seeing here, and also how does it relate to the radio. The contours that you're seeing here are just the X-ray surface brightness contours that I showed you before. So there's some hint of possible correlation between some radio structure and the X-ray temperature. In particular, right over here, this part of the radio relic. There is that radio relic seems to be enhanced right where the temperature is increased near the edge of where this wake of cooler strip gas is associated. So what's going on here? So we expect that for that radio relic in particular, in order for the radio emission to light up, according to the standard thinking, it requires a shock. We have the ability now with the X-ray temperature map and the surface brightness, which is scales with density squared, to actually calculate the pressure. And a shock appears as a discontinuity in pressure. And so what we did is to look at various regions within the cluster to look for evidence of shocks. So the first obvious place we looked is the one in the middle, which is color-coded green in here. And we looked at a strip of pressure running across here like so, where this straight line shows the pressure distribution that we calculated. That's right where we would expect a shock to occur. Well, here is the actual pressure distribution. As you see running across here, it's very smooth. It is decreasing, but there is no sign of a shock, as was previously claimed to exist in this area. So that's rather curious. In fact, we looked elsewhere within the cluster, and there was only one place where there was evidence of a shock, and curiously, it was right to the west of the 3C28 cluster. 3C28 radio source, I should say, not necessarily what I would have expected, but in orange you see the pressure distribution, and there's a jump by more than a factor of 2 in pressure, which would correspond to a Mach number of 2 or 3. So that's very curious indeed. So this cluster has opened up more questions than answers from what we've seen so far. So what we have done is we've discovered this unexpectedly hot region at the center of Abell 115 that was hinted at from previous observations. It's not consistent with a shock. It's broad, it's diffuse, and it looks to us like it is probably a region of enhanced turbulence, which is what you expect when you have these two massive subclusters merging together and they leave behind a turbulent wake. What you're doing is actually converting kinetic energy from the merger into thermal energy, and that's producing a heating in the central region. What about this radio source? Well, damn if I know. This radio source just doesn't look like what one would expect. There's no shocks there. There are these individual radio sources that are embedded within the radio relic, probably producing some of the high-energy electrons and magnetic fields, but how does it relate to the broader structure? It's really hard to be able to tell. Finally, the complex temperature structure. That's the one thing that is consistent with what we find from numerical simulations, these arcs or rings of enhanced temperature. Here is let's see, maybe I have to turn this off in order to be able to play this. Oh no, this movie is not playing. Yeah, it was playing. It was playing when I tested it. Ah, there we go, thank you. So this is a numerical simulation that we've done. This shows temperature. So it's similar to the X-ray temperature map that I've shown. And what you're looking at here are clusters and subclusters that are falling in together. You see lots of bangs that are going on in here. So as these clusters are coming together, cool, darker gas is merging with subclusters. You see shocks that are created. You see heating at the center. You get arcs and rings that are produced. So this very complex temperature structure that we're seeing within Abell 115 is, I think, consistent with the byproduct that we would expect from this kind of merging activity. So I'll stop there. Thank you.
Okay. Hello, everyone. My name is Ben Hoscheit, and I just finished up my undergraduate studies at the University of Wisconsin-Madison. And today I'm going to tell you a little bit about the research I've been doing recently with Professor Amy Barger in the Department of Astronomy at UW. In particular, I'm going to tell you about the recent substantial and growing observational evidence for the fact that we live in a cosmic void region in the large-scale structure of the universe. And then following this, I will move ahead and assess some of the implications of this observational evidence. So as promised, I would start and get right into it. So the observational evidence I will refer to a study done in 2013 by my advisor, Amy Barger, in collaboration with her then graduate student, Ryan Keenan, and also Lynn Cowie at the Institute for Astronomy in Hawaii. And then from here on out, I will refer to them as KBC. So the first thing that they did was they generated a wide area and deep near-infrared selected galaxy catalog. And on the top left image is the different colored regions indicate the different galaxy samples used to construct this catalog. And what they did was they measured these galaxy number counts versus distance moving in these different regions of the sky. And this allowed them, in a sense, to probe the mass density of the local universe as a function of distance. And that's what you see in the top right plot there. The data points indicate the mass density at particular distances measured. And the density contrast just gives you a scale for how to compare this to an average patch of the universe normalized to 1. What they found was that beyond about 1 billion light years, there was a rise in this mass density. And then at about 1.5 billion light years and beyond, they found that this density normalized to a value that was about 1.5 times larger than what was measured locally. So a seemingly unrelated issue, but still an important topic in cosmology, is this so-called tension in the Hubble constant, or H0. For those of you who are not familiar, the Hubble constant describes the rate at which the universe is expanding. It's primarily measured or estimated using 2 different techniques. The first I will refer to as the local technique, and this characterized as using distance ladder-based measurements with Cepheid variable stars and low redshift type 1a supernova. And currently, their best estimate gives a value of 73.24. And then on the contrary, we have this other technique called the cosmic technique. And this takes advantage of cosmic microwave background, or CMB anisotropies. And currently, the best estimate by Planck in 2015 gives a value of about 66.93. And so, in essence, this difference is significant at the 3.4 sigma confidence level. And for those of you who are not familiar, there's about a 3 sigma level cutoff for when this tension becomes interesting. And here we have a 3.4 sigma difference. So this begs the question related to the previous evidence that I just told you about. Could this, in fact, be related to our place in the local universe? So now to try to answer that last question, we first must understand and build a conceptual framework for how a local void would affect the objects within it. So for that, I bring in this pictorial representation on the right. And in essence, objects within the local void are attracted outward to the more dense regions of the universe, giving them a radial pull in that direction. And then different mass density profiles lead to different amounts of this radial pull. So to better understand the effects from our void and the KBC observations, we must ask the following questions. What is the mass density profile of the KBC local void? And then how large is this pull exactly? So to answer those last questions, the following results I will present serve as a demonstration of the effects within our local void. So on the top left plot, we have the KBC data again shown in red. And we fit a parameterization to this data describing the local void. And this again is density contrast versus distance in the local universe. And for here, we assume sphericity in the local void model. And again, this is justified based on the completeness of the sky coverage from KBC. So associated with this density profile is also a corresponding velocity profile, like we just talked about. And the important note is that this local void adds a non-negligible amount of velocity to the contents within it. And intuitively, measurements made on the outside of this local void are correspondingly not affected by the effects of the void. So moving forward to assess the further implications and modeling of this KBC local void, and now that we have a conceptual framework for how exactly a local void would affect the objects within it, we'll tie these ideas back to this tension in the Hubble constant. So as I briefly mentioned, Hubble constant measurements locally take advantage of low redshift type 1a supernova, and they assume a lambda CDM model to model this data. And in the plot on the right is shown in light gray is the SuperCal supernova data set, which is currently being used for local estimations of the Hubble constant. And the darker data points are the binned means of this data set. In addition, the red curve describes the void model prediction for the KBC void. And the plotting range is interesting in the sense that it is the current plotting range used for the best estimate for the local Hubble constant. So some basics for supernova cosmology, if you're not already familiar. We believe that these explosions all release the same amount of energy and therefore magnitude. And this gives us an absolute magnitude reference point from which we can subtract from a measured apparent value for their magnitude from Earth. And this difference, in addition with the redshift data, gives us a sensitive probe for the expansion rate of the universe. So as was discussed, the KBC void mimics a lambda CDM model with a large Hubble constant on scales within the void due to this extra pull. And that is seen in the red curve on the low redshift range. And then on the contrary, outside of the void, it mimics a lambda CDM model with a lower Hubble constant. And in essence, the takeaway point is that the local void distorts the lambda CDM distance redshift relation. So as one can see in the plot on the right,